All right, let's get started with our next analysis. It's analysis number 12. It's record 13. We've highlighted it, so we'll go to add-ins, EasyHas PDB menu, load parameters from PDB record. And we get our parameters loaded in, and this is an excimer laser. What excimers do is they produce UV light, and you can get different wavelengths out of it by using different gas mixes. We commonly find these lasers in laboratory use. Now we've loaded in the parameters. The one thing I would like to point out here is that the ANSI default exposure duration for UV light is 100 seconds. Right? So we have the 100 seconds in. The other thing is these excimers typically put out a rectangular top hat beam, which means we're going to have a major axis, 25 millimeter diameter, 5 milliradian divergence, and a minor axis at 10 millimeter diameter and a 2 milliradian divergence. Right? The other thing about a top hat is that it has uniform irradiance across the beam. So what that means is the 1 over E diameter and the 1 over E squared diameters are the same. And you can see this by looking at the NOHD and the OD values, and we change this parameter to 1 over E squared, and we'll notice there is no change here. Let's put it back to 1 over E. Again, no change. If you do this with the Gaussian beam, you'll see those values change. So 1 over E and 1 over E squared are equivalent with the top hat beam. Let's take a look and see that this is a pretty serious laser. It represents a tremendous hazard to us. OD, worst case, is 6.8. At the observer range of 1 meter, it's an OD of 5.4, and that's because you've got a bigger beam, much bigger beam than the limiting aperture, which is 3.5 millimeters, so that only 3.7% of the power or energy is passing through the limiting aperture. But still, we have an NOHD of over 2,500 meters, 2.5 kilometers. Let's see what the skin is. Well, with the same MPE, kind of expect the nominal skin hazard distance to be the same as the nominal ocular hazard distance, and it is. One other thing I'd like to look at is the time skin MPE. Yeah, it's only about 7 million times above the limit. So you might want to think about what kind of control measures do you want in this lab? And is it only for the user? Let's take a look at the diffuse reflection. The diffuse reflection hazard from this thing is over 4.5 meters, 4.61 meters. So pretty much everybody in the lab could be affected by this laser. So what kind of control measures are you going to have in this lab when you're running this laser? Right? Now, one of the things I pointed out is you can change the gas mix, get a different wavelength out, and one of the wavelengths you can get is 308 nanometers. 308 nanometers has a nickname in the industry as the cataract maker. It's the perfect wavelength to accelerate cataract production on the lens of your eye. When we enter that, we get a message about successive day exposure. So I'm going to answer yes to that because we'll assume that you'll work with this laser today. Tomorrow you'll come in and be exposed again to near the MPE level. Right. So I'm going to say successive day. But let's just go ahead and go to the standard and take a look at what the standard says about successive day. And really it's 8.2.3.1. It gives us some guidelines about multiple pulse exposures. And we'll take a look at that in just a minute. Really what they're saying here is that from 10 seconds to 30,000 seconds, remember, a photochemical effect starts at 10 seconds. So from 10 to 30,000 seconds, the MPE is expressed in radiant exposure, so that the longer exposure time you have, the more reduced the MPE will be, the more restrictive it will be. The other thing it tells us is that from 280 to 400, where our 308 nanometer wavelength lies, for any 24-hour period, you should reduce the MPE by a factor of 2.5 for succeeding days. So what happened when I said yes to successive days is the MPE automatically gets reduced by a factor of 2.5. Let's go back and look at look at our example again, we'll see that this isn't quite as hazardous as the 248 nanometer wavelength, because the NOHD and the OD values are slightly lower. Right? But anyway, that's now if we were to take a look at this again and say, well, let's enter 308, get our message out, and we say no, we'll see that they're even further reduced because we're no longer reducing the MPE. Another wavelength we'd like to look at is 351. This is, can be produced. We'll start off by saying yes, and we'll see this wavelength isn't nearly as hazardous as the other two wavelengths. Okay, but it is certainly presents a hazard. It's 20,000 times the skin MPE. So again, we want to ask ourselves, what kind of control measures do we want to have in place? But do notice here that the NHC is greatly reduced to only about 0.4 of a meter. So we might have a different consideration for when we run this laser if other people in the laboratory, we might not need certain control measures for people in the laboratory when we're running at the wavelength of 351. But if we switch to 248, bigger NHC, a diffuse reflection, we would have different control measures for people in the laboratory. Okay. One last thing we'll do is let me take a look. Let me just go to the table and explain one thing. Let me go to View, Rotate, and this is what the table meant. From 10 to 30,000 seconds, you'll see that for the photochemical effect, photochemical MPE, it is expressed in radiant exposure, joules per square centimeter. So what that tells you is that as the exposure gets longer, your MPE is going to be more reduced. Let me show you how that works. We'll just come over here. Let's look at this MPE, and let's change this exposure. Okay, so it's 4 milliwatts per square centimeter. Let's change the exposure duration to 30,000, and you'll see that yes, the MPE gets reduced because we're at a much longer exposure level. That's one of the reasons you will express the MPE in terms of radiant exposure for wide exposure durations, so that MPE is getting reduced for longer exposures. Okay? All right, that's it for this one.